Okay, hi folks, today we're looking at the charging and discharging graphs for a capacitor with a DC supply. Remember, a capacitor is made of two metal plates with a gap or an insulator between the plates, and no charge crosses between the plates. So if we've got a DC supply here, then electrons will be pushed round from the negative terminal onto one plate, and they will build up on that plate, and electrons will be pulled towards the positive terminal from the other plate, and that will leave that top plate positively charged, and therefore we will have an electric field between the plates and a potential difference across the plates. Now, as it fills up, it becomes more difficult to push more electrons onto the bottom plate when there's already negative charge there, and it also becomes more difficult to pull electrons off the top plate because it's already positively charged. So there's a non-linear movement of charge on and off the capacitor. And charge will only move until the voltage across the capacitor equals the supply voltage. Now, I've drawn this little circuit here, which has got a two-way switch in it. We can move the switch to position A, and the capacitor will charge up, and electrons will move in the direction shown by those red arrows there. Remember, no charge crosses the capacitor between the plates, so electrons are pushed from the negative terminal of the supply onto the bottom plate of the capacitor. So charge moves onto the capacitor as it charges, and electrons will move up through the ammeter onto the bottom plate, and electrons are pulled off the top plate towards the positive terminal. If we want to sketch a couple of graphs of what's happening to the voltage across the capacitor and the current on the ammeter as it's charging, then those graphs would look like this. So the voltage increases quickly at first, and then it levels off as it reaches the supply voltage. The current graph, on the other hand, the current will start off at a high value, because when the capacitor is empty, there's no resistance to charge moving on to the capacitor. So we start off at a high current, and as it fills up, that current will decrease, and then eventually when the capacitor is full, then the current falls to zero when it's fully charged. Now really I should have put a resistor in the charging side of the circuit, and then depending on what the size of that resistor is, we would be able to work out what the initial charging current was just by using Ohm's law. So if we make our supply voltage, let's say 12 volts, and we make our charging resistor, the resistance of the charging side of the circuit, 20 ohms, then our initial reading on the ammeter, the initial charging current, I equals V over R, will be 12 over 20, which is 0.6 amps. That's the maximum current at first. Then as the capacitor fills up, that current will decrease, because as charge builds up on the capacitor, it becomes harder to move more charge onto the plates. So your current eventually will decrease to zero when it's fully charged. So fully charged, the voltage reaches a maximum equal to the supply voltage, and when fully charged, your current falls to zero. So when a capacitor is fully charged, no more current flows. It's a bit like when your mobile phone is fully charged, there's no more current flows onto it. So capacitors will block the flow of DC when the capacitor is fully charged. Now what about the graphs then for when the capacitor is discharging, when it's emptying out? So if we move our switch over to position B, then any charge that's on that capacitor will move off the capacitor, and it has to move off the capacitor in the opposite direction to the way that it moved onto the capacitor. So charge moves off the capacitor in the opposite direction to the way it moved onto the capacitor, so the current will flow in the opposite way through the ammeter. So down through the ammeter in this case, and through the 10 ohm resistor. And if we sketch graphs of the voltage against time When it's discharging, the voltage will decrease from a maximum down to 0. And our current graph, because the current's flowing in the opposite direction, we have a negative maximum current to start with, and that current will decrease to 0 as the capacitor empties out. Again, we can use Ohm's law to work out what that initial current would be. In this case, it's 1.2 amps because it's a 10 ohm resistor. So your initial charging or discharging currents can be found by using Ohm's law, and in this example, since it discharges through a smaller resistor, we're going to have a higher discharging initial current, 1.2 amps, compared to it was 0.6 amps when it was charging. So watch out for that, different resistances in the charging and discharging side of the circuit. Also, it'll discharge quicker if it's a smaller resistor. Right, here's a wee demo that I did about 10 years ago of the voltage and current as seen on a CRO when charging and discharging the capacitor. Okay, we've got a wee quick video this morning just because I tried this with my higher class and nothing would work. So now we've got it working. Hopefully going to be able to show you this in 30 seconds or so. This is graphs of charging and discharging a capacitor. Graphs of the voltage across the capacitor and the current. Okay, let's have a wee look. So we've got a battery. Battery is connected via a variable resistor and an ammeter to a capacitor. Okay, that's the charging side of the circuit. And then through a two-way switch, we can move the switch to the right, and that same capacitor will discharge through the ammeter through this second variable resistor. And the CRO is there to monitor the voltage across the capacitor. So first things first, I'm going to discharge it. Just empty it out. So move the switch to the right. The capacitor is empty, so my spot on my CRO is at the bottom of the screen. That's representing 0 volts. Now, as I charge up the capacitor, it's a 1000 microfarad capacitor. As I charge it up through this variable resistor, a 1 kilo ohm variable resistor, let's watch what happens to the trace on the screen. So I'm ready to charge it up, and there we go. I'm now going to empty it out by switching across to the right hand side. Watch the trace. I'm going to show charging and discharging. These are the voltage graphs. Charging, discharging. Again. Okay. What about the current? What happens to the current when it's charging? Watch this little ammeter here. Here's the current when it's charging. Maximum falls to 0. And then when it's discharging, have a guess? Watch, this is it discharging. So when it's charging, the current is instantly at a maximum and then it gradually falls to 0. Watch. And then when the capacitor discharges, the current flows in the opposite direction. Off the capacitor, falls to 0 again. That's charging and discharging of a capacitor. Oh, other thing. If we want to change the rate at which it charges up, we just need to alter the resistance. Or if we want to alter the rate at which it discharges, we just need to alter the resistance. Bigger values of C and R mean longer charge times. Smaller values of C and R, shorter charge times. There you go. Have a great day now. Now, on a final note then, if we were to continually move the switch between position A and B back and forward, then we would get graphs that would look a wee bit like this. So a voltage graph first. Remember, voltage on the y-axis, time on the x-axis. So as it charges, voltage increases, then it would decrease. Moving the switch, so it's going to alternate between charging and discharging, charging and discharging. That would be the voltage graph when we're continually switching. What about the current graph? Remember, current changes direction, so it's going to start off at a maximum, decrease to 0, then it's going to go negative, and then that's going to repeat, and so on and so on. Charging, discharging. Then it repeats, position A, position B. So by moving the switch back and forward, we're alternating the direction in which the charge can move. And if you alternate between charging and discharging, then charge can move continually, and effectively a current can flow all the time. So capacitors will allow an alternating current or AC electricity to flow, but that's for another day. See you in the next one.